Good morning, everybody. Today is 14th October 2020. The day is Wednesday. My name is Ferhan Mazher, and right now I am with the 10 Matric class. The subject we are studying is Physics 5054. And we are on the chapter number 13 of 10 Matric Physics, and we have started working on electrostatic today. In this video and in this lecture, we are working on the electrostatic potential. Electrostatic potential. That's the main concept on which we will be working. So try to understand this idea. So for example, if you have a charge, suppose here I have a charge, and suppose it's positive. So around it we have an area, a region, where if I bring another charge, it will experience an electrostatic force of attraction or electrostatic force of repulsion. So for this purpose I will use a test charge, a unit positive test charge. So I will take a charged body, let me represent it. This is Q, it is positive, and its unit charge, it is equal to 1 coulomb. So it's a unit positive charge. I will use it as a test charge. So what will happen when I will bring this charge in near this, because this charge is positive and this charge is also positive. So what will happen? They will repel each other. So the test charge, when you bring it inside the electric field. For example, when I will take this test charge and suppose I put it here. So you see, this is my test charge. When I put the test charge in the electric field, this one is also positive and this main charge is also positive. Whose electric field this is? So what will happen? They will repel each other because they both are positive. So this will move in this way due to repulsion. It's positive, so they will repel. So the direction of the electric field is whatever is the direction of the motion of this test charge. For example, if I put the test charge here, suppose, for example, if I put the test charge here in the electric field, it's a positive test charge, it's a unit positive test charge. If you put a test charge here, and you are supposed to observe what will happen with it. Because it's positive, this one is also positive, so they will repel. So what will happen? This will go in this direction. It will be repelled, so it will go in this direction. So it means that the direction of the electric field here, at this point, the direction of the electric field is in this way. So in an electric field, if you want to find out the direction of the electric field, what you do, you take a unit positive charge, we call it test charge, and you put it anywhere in the electric field. So for example, I put it on the A position, and in whatever direction it will move due to the electrostatic force of attraction or maybe electrostatic force of repulsion. In whatever direction it will move, that will be the direction of the electric field at that point. So, do you understand this idea, what I am trying to tell you? Okay. Now, naturally what happens? Naturally this happens that whenever you bring a test charge, whenever you bring a unit charge near this, it is repelled. Because the charge here we suppose is positive. So whenever you try to bring near it, it will be repelled due to the electric field. Due to the electric force of repulsion. This will be repelled. Okay. So if I want to move it, for example, if you want to move it close to the Q, if you take this unit charge and you want to bring it close to this charge body, which is against its electric field, because they both are repelling. So now if you want to take this unit positive charge near it, it will not go there. You have to apply, you have to provide energy to move it near the Q, because naturally they are repelling each other. So if you want to move, for example, if this is outside, suppose this test charge is outside. If the test charge is outside the electric field, we say that it is at a distance, at an infinite distance. If the unit test charge is outside the electric field of that charged body, we say that the distance between them is infinite. Now, if you want to move this test charge from this infinite distance near it, you have to do work. You have to provide energy. Because you see, when I will move it, for example, from this infinite distance, let's say I bring it here, and this is coming in this direction, then I bring it here. You see, this is suppose point A, suppose this is point B, suppose. So what happened here? I applied force, I provided energy, I did work, I pushed this charge, test charge, I applied energy and I pushed it. It entered here in the electric field and I push it further. So the amount of work which you did to move a unit positive charge from infinite distance to a point in the electric field, the work you did on that unit positive charge, that is called the potential at that point. For example, if suppose this is just for your understanding, okay? For example, when you move from infinite to this B point, suppose you did 30 joules work on this unit charge. You did 30 joule work on this unit positive charge to move it from infinity to the point B. So what will be the voltage at the point B? 30 joules per coulomb. The work you did to move the unit positive charge from infinite distance to a certain point inside the electric field, that work per unit charge is called potential, electric potential. Okay, so this is, if somebody asks me what is the electric potential here, let me say this is potential at the point B. So that is equal to the work you did on the unit charge. Okay, so that's Q. Work divided by Q. You understand this thing? Okay. So for example, if somebody asks you, okay, how much is the potential at the point A? So what will be that potential? From infinite distance, you took a unit charge and you applied energy on it. You applied energy, you did work on it and you pushed it. And it entered this electric field and reached the point A. So how much work you did by moving the unit positive charge from infinite distance to the electric field, that work which you did, that is called the voltage at that point. So at this point, what will be the voltage? VA, that will be the work done by you on the unit charge. Work divided by the charge. So that is called the potential. Okay. So electric potential at a point in an electric field is equal to the amount of work done in bringing a unit positive charge from infinity to that point. If W is the work done in moving a positive charge Q from infinity to a certain point in the field, the electric potential V at this point would be given by W by Q. It implies that electric potential is measured relative to some reference point, and like potential energy, we can measure only the change in the potential between 2 points. Electric potential is a scalar quantity. Remember, this is a very important MCQ. Okay? Electric potential is a scalar quantity. Underline this sentence, okay? Electrical potential is a scalar quantity. Its SI unit is volt, V-O-L-T, volt, which is equals to joules per coulomb. If 1 joule of work is done against the electric field in bringing 1 coulomb positive charge from infinity to a point in the electric field, then the potential at that point will be 1 volt. Okay? So, let's consider another thing. As make a correction. Make it as Q, as capital Q, and the charge here is Q. This basically represents this charge. Okay. You understand? Okay. So let's move to another thing. Don't forget this formula. Okay? Voltage is energy work divided by amount of charge. So let's move. Suppose we have 2 parallel plates. And this is one parallel plate and this is the other parallel plate. These are 2 parallel plates. One parallel plate is positively charged, and this parallel plate is negatively charged. So there is electric field. There is electric field between the positive plate and the negative plate. And we know, yesterday we learned it, that the electric field lines start from the positive and they enter into the negative. So the electric field lines, they are always from positive to negative. So between the parallel plates, the electric field lines are uniformly distributed and they are parallel to each other. Only at the ends they will be little bended. So these blue lines are basically representing the electric field lines. So if you have 2 plates, parallel plates, and one plate is positively charged, the other plate is negatively charged, so between them we will have electric field. And the electric field, you know, is represented by imaginary lines. These lines are actually not there, but they are imaginary lines. And yesterday we learned they start from the positive and they go into the negative. So these electric field lines start from the positive and they come to the negative. And they are parallel to each other. The blue lines you can see as I have drawn. So the direction of the electric field is from positive to positively charged body and you place it here. Let's say I take this is point A, I take a charged body Q at the point A. This is point A. It's positively charged. So what I did, I took a positive charge, Q charge, is positive, and I put it between these positive and negative plate. Here we have electric field, I put it on the position A. And you know that the positive charge will always move in the direction of the electric field. If you put the positive charge in the electric field, for example, if the direction of the electric field is in this direction, if you put a positive charge here, it will move in this direction. If the direction of the electric field is in this way, if the direction of the electric field is in this way, if you will take a positive charge body, you put it here, it will go in this way. If the direction of the electric field is downward, if you put the electric charge here, positive charge here, it will go. So the positive charge always move in the same direction as that of the electric field. So when I will put a positive charge here, it will move with the electric field lines. It will move parallel to the electric field in the same direction. So what will happen? It will move. And suppose it reaches here, point B. So what happened here? I took a positive charge, I put it in the electric field between the parallel plates, and what happened? That charged body, positive charged body, but it moved from point A to point B. Okay? So, for example, let's say at this point, what will be the electrostatic potential here? That will be in your previous lecture, what you learned, that the voltage at the point A will be the work done A bata Q. This is what we learned in the previous lecture. The voltage, electrostatic voltage at the point B, that will be the work done B divided by Q. Work done, what do I mean by work done? Is the amount of work which I have to do to move that charge from infinity to that point in the... Okay? So, from here, I can say that the work done is equal to the voltage at the point A multiply Q. And the work done B will be the voltage at B multiply Q. And you know, work done at A, what does this mean? It means if the body is at infinity and you want to move it from that infinity and bring it at point A, the work you do, that is work done A, work A. Okay. So, if you find the difference between them, suppose work done A minus work done B, that will be equals to VA multiply Q minus VB multiply Q. You can take the Q common. This is the difference of energy. Okay? So it will be, you can take the Q common and it will become VA minus VB. So this is the energy. So energy is equals to, so what does this represent? You see, when you move from point A to point B. This much energy will be given out. It will be given out. For example, I can give you an example of the gravitational potential energy. For example, in the gravitational potential energy, try to understand this. Try to understand this. It's very easy but little complicated. Okay. For example, in the gravity, now I'm not talking about the electric field, I'm talking about the gravitational field. For example, this is ground. Okay. And I have a brick. But I have a brick which is lying on the ground. I move this against the gravitational field. For example, I take it to the point A. So the brick is here. Okay. So the brick is here at point A. So I have to do work on it, and that work is stored in it. So let me say that work is WA, and that is equal to M, G, and H. I have a point here. Let me say this is point B. And if I want to move the brick from here to here, I have to work against the gravity. So I have to provide the energy. And when you provide the energy and the body moves against the gravitational field, that energy is stored in the body. So the work done in moving from ground to this point, work done B, that will be equal to mgh. So I am supposing that this height is h and this height is capital H. Okay? So you understand? So when you bring the brick here and you let it go, when you bring the brick at point A and you let it go, and it moves from point A to point B, so it gives out energy. The potential energy will be converted into some other form of energy, for example kinetic, for example heat. So when this will move, it will give out energy, and that energy is equal to the energy at the point A minus energy at the point B. So that energy is given out and we can use it to do work. This same principle is used, for example, in the Tarbela Dam or Bangla Dam. They move the water from a higher point to lower point. From a higher point to lower point, when the water drops, it gives out its potential energy, and that energy is used to run the generator. In the same way, when this charge from a high potential, it will move to a low potential. Here you have to do more work to bring it on point A. From infinity, if you want to bring it on point B, you have to do less work. So it has high voltage, it has low voltage at this point. So when this moves from high voltage to low voltage, this much energy is given out. And that energy can be used to perform some useful work. Okay? So, if I read it from the book, and it's very simple. A body in a gravitational field always tends to move from a point of higher potential energy to a point of lower potential energy. Similarly, when a charge is released in an electric field, it moves from a point of higher potential, say A, to a point at lower potential, say B. If the potential of the point A is VA and that of the point B is VB, the potential energy of the charge at these points will be QVA and QVB, as you can see we have written there. The change in the potential energy of the charge when it moves from point A to point B will be equals to, the change in energy will be equals to how much? Q bracket VA minus VB. If Q is 1 coulomb, then the potential difference between 2 points become equals to the energy supplied by the charge. Thus we define potential difference between 2 points as the energy supplied by a unit charge as it moves from one point to the other in the direction of the field is called the potential difference between the 2 points. If a positive charge is transferred from a point of lower potential to a point of higher potential, against the field direction, energy would have to be supplied. If you move a positive charge against the electric field, you will have to provide the energy. But if the unit charge will move according to or along the electric field, it will give you energy. So this is how this topic is. So I hope that you have understood that electric potential is little difficult concept, but I tried to teach you in a story manner. I hope you have understood. So thank you very much, everybody. Have a good day. God bless you all.